Alright guys, so now we're going to do a little bit more with asymptotes and limits, and then I'm going to do one example, maybe two examples of a limit with some trig, which is going to be pretty sweet. Alright, now I got a secret for you. One of these two doesn't require limits. Let's try the first one. Okay, so let's go y equals 3 minus 4 e to the negative x. So what I need to do to find my limits is there anything that x can't be? Well, no, x can be pretty much anything. So now the only important thing is we need to find the limit as x approaches positive infinity. Alright, well let's do that. Now remember that this is the same thing as 3, that shouldn't be an equal sign there, I'm just taking the limit. 3 minus 4 over e to the x. Now this is very similar to that situation where we were taking the limit of 1 over x, right? Because as x gets really big, this bottom's going to get really big. So I should then be able to take the limit as x approaches infinity of this number. So of 3 would still just be 3, and then 4 over e to the x will be 0. And so I get a final answer of 3. Now what does that mean? Well, it means as x approaches infinity, well, note that if x is infinity, I'm going to get a positive number here, but this positive number is going to get smaller and smaller and smaller as it gets close to 0. So when I do 3 minus 0, it's actually going to be a little less than 3 the whole time. Okay, so what we're going to say, as x approaches infinity, y approaches 3 from the bottom, because it's going to be a little less than 3, because that number will be subtracted off. Alright, let's go ahead and look at the limit as x approaches negative infinity. Let's go the other way. Okay, well this one is a little bit easier, because this one, e, we can just go ahead and put in the negative infinity, because if x is negative infinity, what's going to happen there? Well, I'm going to get 3 minus 4 times e to the infinity, and e to the infinity is pretty much infinity. And so 4 times infinity is still pretty much infinity, and 3 minus infinity would be pretty much negative infinity. So therefore, as x approaches negative infinity, y also approaches negative infinity. And that describes the end behavior. Vertical asymptote on one end, as it is approaching the 3, and on the other end it just keeps on going up and up and up forever. And you know what? I'm okay with that. Alright, well let's go ahead and look at this other one. Natural log of x to the third minus 9x. Well, what I recognize here is that here, this has to be greater than 0, right? You can't take the natural log of 0 or anything less. So what I need to do is, first I need to consider that x to the third minus 9x needs to be greater than 0. I factor that, I get x times x minus x squared minus, sorry, that's a squared, minus 9, and then I get x times x plus 3, x minus 3, and we learned that in these wonderful situations we create a sine diagram. So 0, positive 3 for this one right here, and negative 3 for that one. And so anywhere where it's positive, I'm going to have real values. Anywhere it's negative, I'm not. So let's put in a number. Let's say 1. 1 cubed minus 9 times 1 will give me a negative number. So if I put in 1, I get negative. It should alternate. Now what does that mean? Well, that means that the domain goes from negative 3 to 0, not including, and then it again goes from 3 to infinity. Alright, now because of those domains, it's going to have some kind of asymptotes on the end, because it can't just stop. Alright, so what I would say is that as x approaches negative 3, specifically from the right, y will approach, well, it's positive there, so therefore it has to be going up. So y has to be approaching positive infinity. Alright, as x approaches 0 from the left, It's still positive, so y still has to be approaching positive infinity. And then we'll also have, as x approaches 3 from the right, so right here, still has to be positive, so y has to approach infinity. Now here's the kicker. What happens as x approaches infinity? Well, if I put infinity in there, I'm going to have infinity cubed minus 9 infinity, which essentially means that I'm going to have infinity here because the cubed is so much bigger than 9 times infinity. So I'm going to have the natural log of infinity, which is essentially infinity. It just keeps on going up. As those numbers get bigger and bigger and bigger, so will the function itself. And so there you go. We've got the asymptotes and the end behaviors right there. All right. Now, as promised, let's do a little bit of trig. This is actually really, really cool. Okay, the other stuff, okay, yeah, it's we got to do it. We got to learn a little bit about it. But I want to show you this because this is really cool. And actually, I've seen an IB question where you had to do something similar to this before. Okay, so we're going to do the limit as theta approaches 0 of sine of theta over theta. Now, this presents some problems because sine of theta is 0 and theta is also 0. If theta is 0, then yeah, you get 0 over 0. It's not as simple as the polynomials where we just divide by something and it just kind of gets rid of all our problems. Let's draw a picture. And this is where it gets a little bit crazy. Alright, so I've got O. I'm going to draw my theta. There's theta right there. Okay, we're going to draw one segment that goes like this, and another one that goes right here. Alright, I'm just going to label my points. R, Q, P, T. Nothing special. Nothing special. Nothing. Alright, now actually this one right here, I'm going to draw it so that if I were to draw this triangle right here, I want that to curve right there. Alright, because that's going to be important. So this is R right here. And then Q, that's an R, by the way. And this is a Q down here at the bottom. Okay, this is a right angle, which of course, what does that mean? That means that this right here, if we're assuming a unit circle, okay, unit circle, radius 1, that'll be important. It'll keep it a little bit simpler. This piece right here will be sine of theta, and then OQ will be cosine of theta, right? This should be okay with that. That should be fine. All right. Now, how am I going to get the limit as theta approaches 0 of sine of theta over theta? All right. Well, this is what we're going to do. I've got 3 different things here. I've got an arc right here. So I've got a sector essentially right here. I've got a triangle, and then I've got a sector. I want you to notice that the area of sector ORQ is less than, or I guess you could debate equal to, if for some reason we made this curve so that it was out there. I don't know, debatable whether it's equal to, but just to be on the safe side, is less than or equal to the area of triangle PQO, which will be less than or equal to the area of sector OPT. Everybody okay with that? I hope you are, because you don't have a choice. But you should recognize that this area is smaller than the triangle because it's inside, and the triangle is smaller than the big sector. I mean, we built it that way. Now, why you would ever come up with this, I have absolutely no idea. But just watch what happens. We can get the sector of ORQ, right? That's just 1/2 theta, and then the radius. And the radius of that is cosine of theta squared, right? 1/2 theta r squared. Okay? And I can get the area of the triangle, which is going to be 1/2 the base, which is cosine of theta, times the height, which was sine of theta. Alright, you hanging with me? And then the area of sector OPT, which of course is just similarly 1/2 theta 1 squared, because I created this as a unit circle, so the radius from O to P is 1. O to T is also 1. Alright, let's do a little bit of simplification here. Alright, so what I can do is I can, let's say the 1 squared is going to go away. What else can I do? Let's divide by cosine of theta. Why you would do that? I don't know. Just do it because we can. Now, it's important to recognize here that because I'm in the first quadrant, okay, because I'm in the first quadrant, cosine of theta has to be positive, right? In this first quadrant, cosine of theta is always positive. That's why I don't have to worry about the signs. Weird things aren't going to happen to the signs because cosine of theta is definitely positive in the first quadrant. So what I'm going to end up with is 1/2 theta cosine of theta is less than or equal to 1/2 sine theta, which is less than or equal to 1/2 theta over cosine of theta. Now, what shall I do? I got an idea. Let's multiply by 2 and divide by theta. Why you would do that? I have no idea. But it is going to make this middle section look exactly like this right here, sine of theta over theta. So I'm going to multiply everything by 2 and then divide everything by theta. So that's going to get rid of my 1/2. This divided by theta will give me simply just cosine of theta. This will be sine of theta over theta, and this will be just 1 over cosine of theta. Now, all we've done is a little bit of algebraic manipulation, nothing outside of the realm of normality, other than the fact that the setup's a little bit weird, but makes sense. Alright, and we just kind of put everything together, we rearranged a little bit, and we came up with this. Okay, well, let's now find out what the limit is as theta approaches 0. Well, what do you get for cosine of theta? As theta approaches 0, what is the limit of cosine of theta? Well, it's 1, right? Your graph, you got 1 there, it goes like this, and as you get to 0 from both sides, it's approaching a value of 1. Okay, so that's less than or equal to sine of theta over theta, which is less than or equal to 1 over cosine of theta. So, oh, sorry, this should be the limit as theta approaches 0. I've got to do the limit of that. And if I do the limit of this, again, 1 over cosine theta will be 1 over limit of cosine theta, which is 1, which means that the limit as theta approaches 0 of sine of theta over theta is between 1 and 1. Now, I don't know about you, but I can only think of one number between 1 and 1. Therefore, we can state the limit as theta approaches 0 of the sine of theta over theta is equal to 1. Is that awesome, or is that awesome? Or maybe it's just pretty cool. But I don't know what to say. That's just nuts. Anyway, so pretty cool stuff. Now, how would I use this? Okay, well, let's say that I have the limit as theta approaches 0 of sine of 3 theta over theta. Okay, well, this is obviously not in exactly the right format. My theta here is actually 3 theta, which means the theta on the bottom also needs to be 3 theta. But if I'm going to do that, if I'm going to multiply the bottom by 3, I got to multiply the top by 3. So I'm going to multiply by 3 over 3, which will give me the limit as theta approaches 0 of 3 sine of 3 theta over 3 theta. So now these are the same, which means it fits this. I do have that extra 3, but remember, if I have a constant times a function, I can just pull the constant out. That was the second rule. in our list of rules there. So then I can just say the limit as theta approaches 0, sine of 3 theta over 3 theta is 1. And so I end up with simply 3 times 1, which is 3. And so the answer to this question would therefore just be 3. All right, now you'll see some of that in your homework and you'll get to practice that a little bit. That's all I got for today. That's a lot for a day. So just take some time, make sure to go through this and practice a little bit, and we'll do a little bit more next time. All right, cheers.